Welcome back to our section on cross product. I've got a few more examples that I would like to do with you, and then also a couple of application problems. So for the next example, we are going to compute and sketch I cross J. Now, I and J are our standard unit vectors in the x direction and the y direction. It may be helpful for you to write out what the component form for each of these looks like. I is 1 unit in the x direction, and then 0 in the y, 0 in the z. J is 1 unit in the y direction, 0 in the x, 0 in the z. That is going to be helpful for when we calculate this cross product, because we need all three of those components to put into our matrix. So we're going to set up our 3x3 determinant matrix with our components. And for I get 0 minus 0. For J, I get 0 minus 0. For K, I get 1 minus 0. So it all simplifies down to just K. Now what this means graphically, if we imagine that we've got three-dimensional coordinate system here, X is coming out at us, Y is going horizontally left and right, Z is going vertically up and down. What we've just done is we took vector I, which is 1 unit in the x direction, and vector J, which is 1 unit in the y direction, and we just calculated a vector that is orthogonal to both of them. Well, since everything we do this semester is going to be in what we call a right-handed system, and what that means is if you take your right hand and you put it on your first vector, which is x, and then you curl it towards the second vector, then your thumb will point in the direction of the cross product. So if you imagine curling your right hand from the x-axis to the y-axis, that means it's curling from right to left, your thumb will point up. So in a right-handed system, I cross J is equal to K. It's equal to our standard unit vector in the z direction, because that is what, in a right-handed system, that's orthogonal to both. Now it is true that negative K is also orthogonal to both of them, but that would just be a secondary possible answer. In a right-handed system, we want there to be just one answer. We want this to be a function where there's one input and one output. So we need there to be a primary answer. For our second example, we're going to compute another cross product, but then we're also going to show algebraically that it is in fact orthogonal to the two original vectors. So we're going to compute V cross W for V having components 4, -1, 0, and W having components -2, 0, 5. And we're going to show that V cross W is orthogonal to both V and W. And you may not remember, but there was a way back in the last section where we learned that we could show that two vectors are orthogonal to one another. So first, some more practice here with calculating cross product. We're going to start with the v components, which are 4, -1, 0, and then the w components, which are 2, -2, 0, 5. So for I, I'm going to have -5 minus 0. For j, I'm going to have 20 minus 0. And then for k, I'm going to have 0 minus 2. So v cross w is -5i minus 20j minus 2k. Now to show that this vector is orthogonal to both v and w, what we need to show is that the dot product is 0. When dot product equals 0, that proves that two vectors are orthogonal. And we said earlier in this section, when cross product equals 0, that proves that two vectors are parallel. So now we have a fairly efficient way to check both of them without having to graph them. Check to see whether two vectors are parallel or perpendicular. So remember, dot product is commutative, so it doesn't matter which vector I write first and which vector I write second, but we're going to show really quickly that this vector we just got back is in fact orthogonal to both v and w. So we're going to show that the dot product comes out to be 0. So dot product, remember, says to multiply corresponding components. So there's my I components, my j components, and my k components, and then add the products together. So we've got -20 plus 20 plus 0, which is in fact 0. And we could also do this with w, and we should get 0 with that one as well. So we're going to multiply corresponding components. This time I'm using w, so that -2 times -5 plus 0 times -20 plus 5 times -2. And we get 10 plus 0 plus -10, which is again, in fact, 0. So we are able to actually prove that this vector we're getting back from the cross product is really orthogonal to the two that we put into it. One very common physics application that we use cross product for is for calculating torque. Torque is a measure of a system's tendency to want to spin about an axis. And torque is a vector. Since we use cross product to find it, the result is going to be a vector. The magnitude of the torque vector is called moment, which gives a numeric value in foot-pounds or whatever our units are for our system to want to spin. And then the direction associated with this torque vector gives us the axis that it wants to spin around. And if it's positive, it wants to spin counterclockwise. And if it's negative, it wants to spin clockwise. So we're going to do an example where we have a nut that we want to turn. And I'm probably not going to turn this the right way. But we've got this wrench that we're trying to use to help us turn that nut. So the way that we calculate torque is we do a cross product between a lever arm, which is represented by vector PQ, crossed with a force that we're applying to that lever arm. So our lever arm here, That's actually a physical thing that we can see and manipulate. That is the handle of our wrench. So we need some information for this wrench. And I'm going to say that this thing is 6 inches long, and it's at an angle of 30 degrees. That's enough information to write out the component form for vector PQ. And we could say P is the fixed point and Q is at the other end of our handle. Now we're applying a force on this handle straight down that has a magnitude of 100 pounds. So that's also a direction and a magnitude for our force vector. So both of these vectors, P, Q, and F, are given to us as magnitude and direction. So to calculate the cross product, we're going to have to change them to components. So remember, if we think of this just in 2 dimensions, the way that we get our x components is by doing magnitude times cosine of the angle. And the way that we get our y component is by calculating magnitude times sine of the angle. And that will be true for both of these. So the components for vector PQ are going to be 6 inches, and it's more common in physics to use pounds rather than inches. So I'm actually going to say that that is a half, excuse me, I said pounds, feet instead of inches. I'm going to say that this is 1/2 of a foot. Then our torque will come out in foot-pounds, which is a more common unit to use for torque. So I'm going to have 1/2 cosine theta, or cosine of 30 for my x component, and 1/2 sine of 30 for my y component. And then for my force, it's pointing straight down, which is 270 degrees with a magnitude of 100. So I've got 100 cosine 270, 100 sine 270. And we want to find the cross product between these 2 vectors. So our torque is going to be PQ crossed with F. And if we set it up like a matrix, I'm going to go ahead and simplify these. Cosine of 30 is radical 3 over 2. And we're multiplying that by 1/2, so we'll get radical 3 over 4. Sine of 30 is 1/2. And if we multiply that by its magnitude of 1/2, we get 1/4. And we said earlier that these cross product problems are always going to be in 3 dimensions. But to start with, we have just a 2-dimensional system, so we could just say there's nothing going on in the z direction. And then for our force vector, cosine of 270 is 0. Sine of 270 is -1. When we multiply by our magnitude, we get -100, and nothing going on in the z direction. If we expand this out, we're going to get 0 minus 0 for the I. We are going to get 0 minus 0 for the j. And then for the k, I'm going to get -100 radical 3 over 4 minus 0 for the k, which is -25 radical 3 k. That is our torque. That is the vector that represents our torque. And it tells us 2 things. Just the magnitude for torque gives us moment, which is 25 radical 3. And you could do the magnitude formula on that to confirm. Also, the direction associated with this torque is only in the z direction. That means the z-axis is what we're trying to spin around. It's serving as our axis of revolution. And because it's negative, it's wanting to spin clockwise around the z-axis. So this system has a tendency to want to spin clockwise around the z-axis with a moment of 25 radical 3 foot-pounds which is about 60-ish, I'd say. The last thing in this section, we are going to talk about the triple scalar product. The triple scalar product we had up in our algebraic formulas earlier, but now we're going to talk about actually how to calculate it and what it's used for. So as long as the three vectors that we're using don't all lie within the same plane, then the triple scalar product is going to give us the volume of the parallelepiped that has the three given vectors as adjacent sides. And a parallelepiped is a three-dimensional parallelogram. I'm going to make a horrible attempt at drawing this, which usually fails miserably, but I'm going to try. So if we have three vectors in different planes, and we imagine those as the the three non-parallel sides, and we try to make parallelograms between them, three-dimensional parallelograms. So you imagine this box here, but what's special about this box is that all of the sides, they don't have to be perfect squares or rectangles. They could be parallelograms. So we've got these parallelogram sides. This is actually a little bit better than I usually do, but still not beautiful. So the triple scalar product requires three vectors, and we talked about kind of the intricacies of this calculation here. You could treat this as two separate problems, where first you do the cross product, and then once you get that answer, you'll take it and do the dot product. But you really could calculate all of this at once by replacing your IJK row in your matrix with your U components. So this one also we could do just in one single calculation using a 3x3 matrix. So in my first row, I'm going to put the components of my first vector. Second row is the second vector. Then the third row is your third vector. So one of the major differences in this calculation is that we're not going to get a new vector back because we don't have IJK in that first row. We're going to be able to calculate this all the way down to just a single constant. But even without the IJK, we still perform that cofactor expansion exactly the same. So let's try an example. We are going to calculate U dotted with V cross W. For U equals, let's say, 5, 1, negative 2. V equals 0, 9, 3. And W equals negative 1, negative 2, 5. So we could throw all of this into just one single calculation using one single matrix, but instead of our IJK row, we're going to put the components for U. So 5, 1, negative 2, 0, 9, 3, negative 1, negative 2, 5. And the cofactor expansion is exactly the same. The only difference is we're not going to see the IJK. So start with the first entry in your first row, block off its column and its row, and when we do that, what we have left is this 2x2 matrix 9, 3, negative 1, 5. And then move to your second entry. Let me erase this stuff so it's not in our way. Then we're going to move to the second entry in that row. And remember, you always change the sign as you jump from term to term. You're going to block off the row and the column for that entry and look and see what you have left. And you will have these 4 elements, 0, 3, negative 1, 5. And then we'll jump to our last entry, which is negative 2. Ignore 2's row and 2's column, and you're left with those. So flip your sign again back to positive, but it's a negative, it's plus a negative 2. And our 2 by 2 matrix is 0, 9, negative 1, negative 1. And then we have to do those 2 by 2 determinants. So I get 5 times 45 minus negative 3 minus 1 times 0 minus negative 3. Plus a negative 2 is the same as a minus 2, and that would be 0 minus negative 9. So that's 5 times 48 minus 1 times 3 minus 2 times 9. And we get 240 minus 3 minus 18, so 219, I believe. That should be right. So what this has given us, if we imagine those 3 vectors, u, v, and w, being drawn in 3-dimensional space, and we were to make all of the parallelograms between them, it would make this parallelepiped, which is just a box with parallelogram sides, and that box would have a volume of 219 cubic units.